Hello. So the first page here is a brief review of what we talked about in section 5.2. So in section 5.2, we talked about the words and, or, and not. All right. So example one here, researchers asked residents of 3 cities to name their favorite mode of transportation. The results are summarized in the table below. We have 3 cities, and then we have 3 favorite modes of transportation: car, train, and plane. Part A, if one person is selected, find the probability that the person prefers travel by plane. Okay, so notation-wise, we're looking for probability that the person prefers plane. All right, so the bottom is going to be the total of everybody. The total here is going to be 80. And then for the top, how many people prefer travel by plane? 12, 10, and 17. 39. Part B, if one person is selected, find a probability that the person is from Los Angeles and prefers travel by plane. All right, so keyword here is and. Notation, what I'm looking for is probability Los Angeles, so LA, and prefers travel by plane. The bottom is going to be the same as the part A, so it's going to be everybody, so everybody is 80. And remember, the word and means both at the same time. So how many people are from LA and at the same time prefer travel by plane? It would be these 17 people. Part C, if one person is selected, find a probability that the person is from San Francisco or prefers travel by train. Keyword here is or. Notation wise, we are looking for San Francisco, so SF, or prefers travel by train. The bottom is still going to be the total, which is going to be 80. Now, or means SF, or train, or both. What we did in section 5.2 was I'm going to take all my SF numbers, which are 5, 9, and 10. And then I'm also going to include my train numbers, which is 15, 9, and 6. But I'm not going to count the 9 again because the 9 I already got when I counted the San Francisco numbers. So I just need 15 and 6. So 5, 9, 10, 15, and 6, that's 45. Part D, if one person is selected, find a probability that the person's favorite mode of transportation is not by car. Okay, notation wise, we want not car. Bottom is going to be 80, just like before. Okay, the top, I want the not car numbers, which would be these 2 columns. So 15, 9, 6, 12, 10, 17, 69. All right, that was a brief review of what we talked about in section 5.2. Not, or, and. The first new thing we're going to talk about today is conditional probability. The notation for conditional probability is this. So let me rewrite this. The way you read this is probability of A given that B already occurred. Okay, so the line stands for the word given. And what you're actually, what this represents is, like I said, the probability of A given that B already occurred. In other words, what's the probability of A if you knew now additional information that B already occurred? All right, so let's do some examples to see how this actually works out. Part E, so we're talking about the same table as the first page. If one person is selected, find the probability that the person prefers travel by car, given that the person is from San Francisco. Notation, probability car, given that the person is from San Francisco. So given line San Francisco. Now, what does this mean? So because I'm telling you additional information that the person is from San Francisco, so you already know that the person is from San Francisco, which means when you calculate the probability, you're going to just restrict yourself to just the San Francisco people. Okay? So what this really means is, for the top and for the bottom, you're just going to focus on the given part, which is the San Francisco numbers, for the top and the bottom. Okay, so let's start with the bottom. So the bottom should be the total of San Francisco numbers. So total for San Francisco would be 5, 9, and 10, which is 24. And then still focusing on just the San Francisco numbers, how many prefer travel by car? Okay, so still focusing on just the San Francisco numbers, how many prefer travel by car? 5. Part F, if one person is selected, find the probability that the person is from San Francisco, given that the person prefers travel by car. Okay, notation wise, this is saying I want San Francisco given car. Okay, so because I have additional information that the person prefers travel by car, I can just focus on the car numbers for the top and the bottom. Okay, so whatever is given, those are the numbers you're going to focus on for the top and for the bottom. So just focusing on the car numbers, how many are there total? So just the car numbers, how many are there total? 11. And then once again, just focusing on the car numbers, how many are San Francisco? So just the car numbers, how many are San Francisco? 5. Okay, let's take a step back here and take a look at E and F. So E and F, part E is car given San Francisco. Part F is San Francisco given car. So what I wanted to point out for E and F is to ask you, does the order matter? So car given SF, SF given car. Does the order matter? Yes, it does, right? Because you get 2 different answers. All right, part G, if one person is selected, find the probability that the person is from Los Angeles, given that the person prefers travel by train. So notation wise, we want LA given train. For the top and for the bottom, I should be focusing on what numbers? Train. All right, so just focusing on the train numbers, what is the total? So just the train numbers, the total is going to be 30. And then once again, just focusing on the train numbers, how many are from LA? So just on the train numbers, how many are LA? 6. In section 5.2, we had an addition rule, which was a formula for calculating the probability of A or B. In this section, we have a multiplication rule, which is going to be a formula for calculating P of A and B. Okay, and as it sounds, what you're going to do is you're going to multiply. So it's not going to be quite probability of A times probability of B, but it's close. So to find probability of A and B, it's going to be probability of A times probability of not just B, but probability of B given that you know A already occurred. All right, and then let's talk about how we're actually going to use this. So part H, if two people are randomly selected, what is the probability that the first person prefers travel by plane and the second person also prefers travel by plane? Okay, notice that now I'm asking about two people. Okay, everything I've asked you before was about one person. Okay, so what the multiplication rule is going to tell us to do is we're going to do it as two separate fractions, and then we're going to multiply. Okay, so that's the multiplication rule part of it. Because we're talking about two people, it's going to be two fractions. Okay, the first fraction I want to be the first person prefers travel by plane, so I want the first person to be plane, and then the second person also by plane. So the second person also by plane. Okay, so let's take a look at the first fraction. So first fraction is going to be the same as what we've been doing before. Okay, so what's the probability that you get a person who prefers travel by plane? Well, the bottom is going to be the total of everybody. Okay, so everybody is going to be 80. And then how many people prefer travel by plane? 12, 10, 17. That's 39. Right, so that takes care of this part, probability of A. Now, for the second fraction, this is where we have to take care of the given A part. So for the second fraction, we have to keep in mind that we already chose one person that liked plane already. Okay, so because of that, for the bottom, we don't have the full 80 anymore, right? Because we chose one person already, which means the total we have left is not going to be 80, it's going to be 79. And then how many people prefer travel by plane? Keeping in mind that I have one person who prefers travel by plane already in this first lot. So how many people prefer travel by plane? It's 39, right? But keeping in mind that I already have a person who prefer travel by plane already, I'm now down to actually 38. All right, and then part I. If two people are random selected, what is the probability that the first person is a person from LA who prefers travel by train, and the second person is from San Francisco? Okay, we're talking about two people, which means we should have two fractions. First fraction, first person from LA who prefers travel by train. So first person I want to be LA train. Second person is from San Francisco. So second person is anybody from San Francisco. First fraction, the bottom is going to be out of everybody again, which is going to be 80. And then how many people who are from LA prefer travel by train? So how many people from LA and train? So LA and train would be 6. Now, second fraction, we have to keep in mind what we chose in the first lot, right? So for the second fraction, we already chose one person, which means the bottom is going to be one less, so 79. And then how many people are from San Francisco? So San Francisco is 5, 9, and 10, which is 24. And we have to ask yourself, is it going to be 24 or is it going to be 1 less 23? Okay, so ask yourself, have we already used anybody from San Francisco yet? No, right? So the first slot was LA train. So we haven't used anybody from San Francisco. So we should have the full 24 here. Okay, so take a look at H and I and make sure you understand why for part H I had to reduce and for part I did not. Okay, so for part H, I had to reduce that by 1 down by 1 to 38 because I already used somebody by plain, somebody who prefers plain already, right? Which means I had to reduce it by 1. For part I didn't have to reduce because I didn't use anybody from San Francisco in the first lot. All right, part J. If 3 people are randomly selected, what is the probability that the first person is a person from San Francisco who prefers travel by plane? The second person is a person from LA who prefers travel by plane, and the third person prefers travel by plane. Okay, we're talking about 3 people here, which means I'm going to need 3 fractions. Okay, first fraction, first person, I want to be San Francisco who prefers travel by plane. So first fraction, I want to be SF, plane. Second person, LA, who prefers travel by plane. So second person is going to be LA, plane. And then third person prefers travel by plane. So third person is from anywhere, plane. So third person is just regular plane. First fraction. First fraction, the bottom should be the total of everybody, which is going to be 80. And then for the top, how many people from San Francisco prefer travel by plane? So how many San Francisco and plane? San Francisco plane would be 10. All right, second fraction. All right, keeping in mind that we already chose 1 person, which means the bottom of the second fraction should go down by 1. And then for the top, LA plane. So LA plane would be 17. Okay, so we have to decide, is it going to be 17 or is it going to be 16? And the way you decide is ask yourself, have you used LA plane yet? We did not, right? We used SF plane, but we didn't use any LA plane yet. So this one should be the full 17. Third fraction, okay, the bottom's going to be reduced by 1 again because we chose 2 people already. So we should be down by 2, which means we're now at 78 for the total. And then plane. Plane together is 12, 10, 17, which is 39. But you have to ask yourself, have you used any plane numbers yet? And you have, right? You use plane numbers in the first slot and you use plane numbers in the second slot. So we're actually down by 2. So this should be 37. So not 39, not 38, but 37. Because we used 2 planes already, right? This one SF plane, which is a plane. This one LA plane, which is plane. So we should reduce it by 2. Part K. If 3 people are randomly selected, what is the probability that the first person is a person from Sacramento who prefers travel by car? Second person is from LA who prefers travel by train, and the third person prefers travel by car. Okay, 3 people, so 3 fractions. First person, I want to be Sacramento car. Second person is Los Angeles who prefers travel by train, so LA train. Third person prefers travel by car. So third person is just regular car. Okay, no city. All right, first fraction, bottom's going to be everybody, which is 80. Sacramento car. Sacramento car Sacramento car 6. Second fraction, the bottom, we're down by 1, so we should be at 79. LA train 6. Third fraction, for the bottom, we're down by 1 again, so we're now at 78. And then car. Okay, car is 650. 650 is 11, but we have to ask yourself, did we use any cars yet? I used a car in the first slot, right? I used SAC car. So we're actually down by 1 for the total cars. So it's not going to be 11. It's actually going to be 10. Okay. And then technically, for these fractions, we should multiply them and then get a decimal and then percent. But for lab assignments, you can just leave them as fractions like that. All right, solving at least one problem using complements. Let's take a look at L first. So L says, if 3 people are randomly selected, find the probability that at least one person is from Sacramento. Okay, so keyword here is at least one. Okay, so what does at least one mean? If I talk about 3 people and I want at least one of them to be from Sacramento, what does that mean? At least one means one or more, right? So it could mean 1 person from Sacramento. It could mean 2 persons from Sacramento. It could mean 3 persons from Sacramento, right? All of those count as at least one. So calculating at least one probabilities directly is going to be hard, right? Because at least one could mean 1, it could mean 2, it could mean 3. Okay, so you would have to do those separately and add them up. And even worse, I said it could mean 1, right? But what does 1 mean? It could mean that the first person is from Sacramento and the other 2 are not. It could mean that the second person from Sacramento and the other 2 are not. Or it could mean the third person from Sacramento and the other 2 are not. Okay, so you would have to take into account those possibilities. It could mean 2 people are from Sacramento, right? There's many possibilities there also, right? It could mean that the first 2 are from Sacramento and then the third person is not. It could mean the first and last person is from Sacramento and the middle person is not. It could mean the last 2 are from Sacramento and the first person is not. So if you're going to calculate at least one directly, you would have to take into account all of those possibilities. Calculate the probabilities separately and then add them up. Okay, that's the hard way to do it. So we're not going to do it that way. We're going to use the complement. All right, so what is the complement of at least one? So let me okay. If I wrote those numbers 0, 1, 2, 3, 4, 5, 6. When I say at least one, which numbers do I mean? Numbers that are at least 1. Okay, at least 1 means 1 or more. So at least 1 would mean 1, 2, 3, 4, 5, 6. Okay, all of those numbers are at least 1. Which means what number is not at least 1? 0. Okay, so the key point I want to make here is that the complement of at least 1 is none. Okay, so that's one fact. And then the other fact I'm going to need is, remember in 5.2 we talked about probability of the complement is 1 minus the probability of the regular event, okay, or vice versa. Which means the way you calculate probability of at least 1 is to do it 1 minus probability of none. Okay, and that's going to be the easy way to do it. Okay, let's do this for part L. If 3 people are randomly selected, find a probability that at least one person is from Sacramento. All right, so let me set this up. So I want probability at least one Sacramento. Okay. The easy way to do that is to do 1 minus probability none from Sacramento. And so what I need to calculate is this one. So 1 minus, and I want to calculate the probability that if I pick 3 people, none of them are from Sacramento. Okay? So 3 people means 3 fractions. And when I say none Sacramento, I mean not Sacramento, not Sacramento, not Sacramento, right? So I want all of these to be not Sacramento. Okay, so three people, I want all of them to be not Sacramento. First fraction, the bottom should be the total, which I think is 80. And then how many people are not from Sacramento? So not Sacramento would be the bottom 2 rows. So 5, 9, 10, and then 6 and 17. I got 47. Okay. And then I want the second person to also be not Sacramento. Okay. Once again, I should be down by 1 for the bottom. And actually, let's do the third one also. So third bottom is going to be 78, down by 1 again. Okay, so not Sacramento. Second person also not Sacramento. So not Sacramento we said was 47, which means the second not Sacramento should be down by 1. It's going to be 46, and then 45. And then that's the probability. 1 minus 47 over 80 times 46 over 79 times 45 over 78. Part M. If 3 people are randomly selected, find a probability that at least one person prefers travel by train. Okay, so I'm trying to calculate at least one train. The easy way to do at least one train is to do 1 minus probability none train. And I have to calculate that probability. So how many fractions do I need here? We're talking about 3 people, so 3 fractions. Okay, and none train means I want not train, not train, not train. So I want all of them to be not train. Okay, first fraction is going to be out of 80, because that's the total from everybody. And then second fraction, the bottom is going to go down by 1. And then the third fraction by 1 again, so 78. Okay, top. How many people are not trained? Not trained would be 6, 5, 0, 12, 10, 17. Okay, second fraction, also not trained. But keep in mind, we already have not trained already, so we should be down by 1. 49. And then once again, for the same reason, down by 1 again, 48. Part N. If 3 people are random selected, find a probability that all 3 prefer travel by train or by plane. Okay. Notice that this one is not at least one, right? Part L and part M were both at least one problems. Okay, if it's an at least one problem, you're going to set it up as 1 minus probability of none. Part N is not an at least one problem. Part N is just a regular 3 people problem. So this one is not going to be 1 minus none. This one you just do it the same way we did on the previous page. And this one I want all three preferred travel by plane. So I want plane, plane, and plane. Okay, so this is just a regular 3-person probability from the previous page. Bottom of the first fraction is going to be 80, the total, and then it's going to go down. Up top, how many people prefer travel by plane? Plane is going to be 12, 10, 17, so 12, 10, 17, which is 39. Second fraction, plane again, but keep in mind that I already used the plane already, so we should be down to 38. And then for the same reason, we should go down again to 37 because we used 2 planes already. So we should be down by 2. Mutually exclusive events is something we talked about in section 5.2. So let me remind you what that means. 2 events are mutually exclusive. So A and B are mutually exclusive if they cannot happen at the same time. Okay, and that was the word definition that we talked about in section 5.2. So we also talked about a math definition, which let me remind you what that is. Okay. Whenever you see the word mutually exclusive, you should be thinking of the and. Okay. So A and B are mutually exclusive means probability of A and B. Okay, remember, probability of A and B is the probability of A and B both happening at the same time. And if they cannot happen at the same time, then their probability is 0. Okay. So that was from section 5.2. Okay, the new concept in this section is independent. Okay, so let me tell you the word definition of independent, and then we'll also talk about the math definition. Okay, so independent okay, so A and B are independent if basically if one has nothing to do with the other. So if the occurrence of one does not affect the occurrence of the other. And dependent just means not independent. So I'm going to use the words independent and not independent. And then you can also use the word dependent for not independent. All right, so there is also going to be a math definition, which I'm going to come back to later. So let's first use the word definition to talk about some examples. Determine whether the following pairs of events are independent or dependent. Okay. First example here. Flipping a coin, rolling a die. Okay. So here's a coin. Here's a die. Does getting a head on a coin affect what happens on the dice? Does getting a tails on a coin affect what happens on the dice? It doesn't, right? So whatever happens on a coin has no effect on what happens on a dice, and vice versa. So flipping a coin and rolling a die is independent. Being kind and having many friends. So does being a nice person affect whether or not you have many friends? It probably does, right? Because if you're a jerk, you probably don't have a lot of friends. So these do affect each other. Okay, so we would say that they are not independent. Or you can use the word dependent here. Once again, I'm gonna use the words independent and not independent. Part 3. Drawing a card from deck, getting a queen, not replacing it, and then drawing a second card. Okay, so you take a deck of cards. All right, take a deck of cards. You take out a queen. Take out a queen. Okay, so pretend I shuffled, and then I got a queen. Okay, not putting it back, and then drawing a second card. So does getting a queen for that first card affect whether or not I get a queen on a second card? Yes, it does. Right? Because I'm not putting it back, that means I have one less queen to work with for that second draw. Okay, so usually in the deck of cards there's 4 queens, so now there's 3 queens. Okay, so it does affect what happens. So this would be a not independent. Now compare that with part 4, which says drawing a card from deck, getting a queen, putting it back, shuffling it again, and then drawing a second card. So this one would be independent because the fact that you're putting it back and then shuffling it, that really just resets everything. Okay? So this one would be independent. Okay, so these two are pretty important examples. So part 3 is sampling without replacement. So you're taking a sample and then you're not putting things back, which means it is going to affect your next pick. Okay, so that's going to be not independent. Part 4 is typically called sampling with replacement. Okay, because you're putting things back and reshuffling, that really just resets the situation. Okay, which means whatever happened in the first pick doesn't affect the second pick, right? Because you put things back and then you reset everything. Okay, so sampling without replacement is not independent, and then sampling with replacement is independent. And then last example here, studying hard and getting good grades. So does studying hard affect whether or not you get good grades? It probably does affect, right? So this one would be not independent. So once again, independent means one thing has no effect on whether the other thing happens or not. Okay, they don't have anything to do with each other. They don't affect each other. Okay, so that's the word definition of independent. Now let's talk about the math definition. Okay, so what does it mean when the occurrence of one does not affect the occurrence of the other? Okay, so I'm going to write one down, and then I'll tell you what it means. Okay, so probability of A is equal to probability of A given B. Now, remember, probability of A given B means probability of A given that you know that B already happened. So what this is saying is that the probability of A is the same as probability of A knowing that B happened. In other words, adding extra knowledge that B happened does not affect the probability of A. You get the same answer. Right? Probability of A regular versus probability of A with extra knowledge that B happened already. You get the same answer. Okay, so that's mathematically what it means for independence. Adding that extra given B doesn't change the answer, right? Adding that extra given B gets you the same answer as regular probability of A. Okay, so that's one definition that you can use. Now, there's two other criteria that you can use, and I'll write them here. Okay, the second criteria is going to be the same as this, except you just swap A and B. So this would say that probability of B is the same as probability of B given A. Okay, so adding on a given A doesn't change the answer of probability of B. Okay, the third criteria is that probability of A and B is the same as probability of A times probability of B. Okay, and that comes from this multiplication rule that we talked about on page 3. So this is always true. So probability of A is equal to probability of A times probability of B given A. If A and B are independent, then probability of B given A is going to be probability of B. So if you know that A and B are independent, then you can replace this part with just regular probability of B, which gets you this. Okay, so what I want to say here is I almost don't even want to write that last one, because this last one you should only use. Okay, so let me write this here. So only use this last one if you know that A and B are independent. Or if you're checking independence, or okay, in other words, if in the problem it doesn't say the word independent anywhere, you should not use this. Okay, you should be using the regular multiplication rule, which has that given part. Okay, so there's 3 criteria you can use to check whether two events are independent. It doesn't matter which one you use. For simplicity, I'm always going to probably use that first one, but technically you could use either one to check, either of these 3 to check. All right, so let's see how to use those definitions in an example. Okay, so same example with the table on that first page. Part O. Let A be the event that the person is from Sacramento. Let B be the event that the person prefers travel by plane. Are A and B independent? Explain. Okay, what I mean by explain is we're talking about independent, which means it's these 3 criteria. Pick one of them and check it. Okay, so like I said, I'm always going to pick that first one. I'm usually going to always pick that first one. So that first one says P of A equals P of A given B. Okay, so we're going to check. P of A equals P of A given B. And then let me replace A and B with what we're talking about in this problem. P of A means P of A means Sacramento, so P of Sac equals P of A was Sac given B was plane. Okay, probability of Sacramento equals probability of Sacramento given plane. And then all we're going to do is calculate each probability, the left side and the right side, and then check whether or not they're equal. Okay, so the left side we know how to do. The right side we also know how to do. Okay, let's start with the left side. Left side is probability of Sac, so that's just regular probability of getting a person from Sacramento. The bottom is going to be the total, which is 80. Okay, the top is going to be from Sacramento. So people from Sacramento. Sacramento would be 6, 15, and 12. So 6, 15, and 12 is 33. Okay, that's the left side. The right side is Sac given plane. Right, so remember, this is what we talked about today, right? Sac given plane, I should be focusing on the given, right? I should be focused on just the plane numbers for the top and the bottom. Okay, so focusing just on the plane numbers, how many are there total? Just the plane numbers 12, 10, 17. The total would be 39. And then just focusing on the plane numbers, how many are from Sac? So just the plane numbers, how many are from Sac? 12. And that's the right side. So 12 over 39 is Sac given plane. 33 over 80 is just probability of Sac. Okay, so I am going to compute this out just to check. So we're checking whether or not these two things are equal. So 33 over 80 is 0.413. 12 over 39 is 0.308. Okay. So what is the conclusion? Are A and B independent? Okay, if they're equal, they're independent. If they're not equal, they're not independent. So our conclusion here is not independent. And when I say explain, I want this calculation. Okay, tell me what you're checking. Check the left side, check the right side, and then check whether or not they're equal. Part P. Let A be the event that the person prefers travel by car. Let B be the event that the person is from Los Angeles. Are A and B mutually exclusive? All right, so notice that in part O, I was asking about independent. Part P, I'm asking about mutually exclusive. So for mutually exclusive, which is this one, you should be checking this. Okay? So we should be checking whether the and is equal to 0. And let me replace A and B with what we're talking about in this problem. A here is car. B is LA. Okay, so check left side, check right side. Right side's already 0, so that's nothing to check there. Left side, probability of car and LA. Okay, so this is and, so probability that the person is from LA and at the same time prefer car. The bottom here is going to be everybody, so it should be 80. So one thing I didn't say before, but I probably should have said is, if there's a given, the word given, the bottom is not going to be the total, right? Because you're focusing on a certain part of the table. If you don't see the word given anywhere, then the bottom will be the total. Okay, so here is, we're talking about and, so we're not talking about given anything. So the bottom should be the total. Okay, the top, car in LA. So how many people like car and are at the same time from LA? So car LA would be 0. All right, 0 over 80 is 0. Okay, left side 0, right side 0. They are equal. So your conclusion, they are mutually exclusive. Okay, if they're equal to each other, it's mutually exclusive. If they're not equal to each other, it's not mutually exclusive. Part Q. Let A be the event that the person prefers travel by train. Let B be the event that the person is from San Francisco. Are A and B independent? All right, so what are we checking here? We're talking about independent, right? So we should be checking one of these three things. I'm going to pick that first one. So we're going to check P of A equals P of A given B. All right, I'm going to replace A and B with what we're talking about in this problem here. A is train. On the right side, it's A given B, so that's going to be train given B was San Francisco. All right, so check the left side, check the right side. Left side is probability of train, so that should be regular probability of train. The bottom's going to be everybody, which was 80. And then how many people like train? Train was 1596. 1596 is 30. On the right side, we're talking about train given SF. Okay, so this one, we should be focusing on SF for both the top and the bottom. All right, so focusing on just the SF numbers, how many are there total? So just SF numbers, 5, 9, 10. Total is 24. Okay, still focusing on just the SF numbers, how many are train? So just SF numbers, train would be 9. Check the left, check the right, and check whether or not they're equal. So 30 over 80 is 0.375. 9 over 24, 0.375. Okay. Conclusion, they are independent. Part R. Let A be the event that the person is from San Francisco. Let B be the event that the person prefers travel by plane. Are A and B mutually exclusive? Okay, so this one is now talking about mutually exclusive. Mutually exclusive, you should be checking the and. Right, mutually exclusive, you should be checking that. So we're checking P of A and B equal to 0. I'm going to replace A and B with what we're talking about here. A stood for San Francisco. B stood for plane. Check left side, check right side. Right side's easy, it's already 0. Left side, SF and plane. This is not a given problem, so the bottom should be the total. Top number, how many people like S or from SF and at the same time like plane? So SF and plane, SF, plane 10. All right, 10 out of 80 is definitely not 0. You don't really need to check this one. Okay. Left side is 0.125, right side 0. They're not equal, which means it's not mutually exclusive.